Hello, welcome back to Map 332 Linear Algebra, and welcome to the second part of the presentation on sections 2.3, where we'll continue to discuss some of the very basic properties for determinants. So in the first part of the presentations, we talk about a very important theorem, which states that for a matrix that is invertible, that matrix will have determinant that is not equal to 0. So in this video, we are going to look at what happens when you have invertible matrix with determinant not equal to 0. We can actually write down a formulas to find the inverse. So this is a closed form formula. It's not kind of like the procedures where we learned last time when we try to take a matrix and row reduces it to the identity matrix, and by doing so find the inverse. Now this time we are not going to do any row reduction. Instead we have formulas to compute the inverse for our invertible matrix. And after that, we are also going to introduce another method, which is solving a system of linear equation without doing row reductions. And again, this time we also have a closed form formulas. We have a formulas to compute the unknown for a system of linear equations without doing row reductions. So that is called the Cramer's rule, and we'll see how it's done. And so let's get right to it. All right, let's begin by looking at the objective for this section. So at the end of this video, you should know how to compute the inverse of a matrix using the adjoint methods. And you need to also understand why this methods works. And at the very end, you should know how to solve system of linear equations using something that we call Cramer's rule. Okay, let's recall how we compute the inverse of a matrix last time. So let's say this is our matrix A. So you have matrix A and you want to find the inverse of this matrix. What we do is we construct this augmented matrix. As you can see, this is our A and this is our identity matrix. And the theory is that if you can row reduce, so when you do the row operation, you have to do it the entire row like this, not just on A, but also on I. So the theory is that if you manage to do the row reductions all the ways to this, so if you can turn this part here to identity matrix, then whatever matrix that you have right here, this is actually the inverse of A. So this is actually the inverse of A, and we actually know how these methods and why these methods works. It relies a lot on the elementary matrices and stuff like that. So as you can see in these situations here, we can actually row reduce it to an identity matrix, and then this matrix is going to be the inverse of A. So this is A inverse. Okay, now, so this method works very well. You can use your calculator, the websites, the row reduction websites, to row reduces matrices like that very easily. However, for some matrices, this type of row reductions is not going to work. For example, we have also seen a matrix like that before. So if you remember from the previous video, this is the standard matrix which represents rotations. And rotations in R3, right? So we do have a matrix that looks like this, and this is actually significant. This is not any arbitrary matrix. This is actually a matrix that is important in applications. And the question is that I want to find the inverse of this matrix. And if you follow the row reduction procedures, you will see that it's a problem, because when we row reduce, we usually want it to have numbers, but this is not numbers. So in order to turn this to 1 and get rid of this, get rid of that, that operation is going to be very complicated, super tedious, and you don't want to do row reductions when your matrix actually have like a symbols, like something that is not a number, so things will be very complicated. So there is actually another way to write down the formulas for the inverse. And this is also something that is nice in the sense that to find the inverse of a matrix here, basically here when people ask you, how do you find the inverse? You have to describe a process, right? So this is more on a process. So you have to like, oh, do row reduction, do this, do that. So this is more procedural, right? So you have to tell people a process. And sometimes we don't really want that. We want a formula. So let's say, for example, A is this, right? So what's A inverse? So you want to write down A inverse equal to something. So this is, you want it to be more like a formula. So we do know that such formula exists because we know the inverse of a 2 by 2 matrix. So for example, if you have A equals to A, B, C, D, and then we know that if the determinant of A is not equal to 0, then A inverse actually have a formula is 1 over the determinant of A. And then what you do is that you interchange these diagonal entries, and then the thing that is off diagonal, you don't interchange them, but instead you change the sign. So this is actually, so a lot of you have seen this kind of formula before. So this is actually the formula for A inverse using the adjoint methods. Okay, so this is something that is easy. Most of you have seen it in high school algebra. And we can also actually develop a formula like that for all the n by n square matrices. And that method is called the adjoint methods. So before we talk about the method, we will have to talk about some terminology, okay? So in the very first video, in chapter 2, when we talk about how to compute the inverse using the cofactor expansion, so you already know what is a cofactor. So cofactor, okay, so cofactor for positions for entries ij is going to be -1 to the power of I plus j, and then multiply the minor ij. And minor ij is the determinant for a submatrix after you deleted the I row and the j column. So we know all that before. And so let's say you have a matrix A, all right? So this matrix A here, right? So this matrix here, A here, will have positions, entries A11, A12, all the way to A1n. And then here you have AN1, AN2, all the way to ANN. So remember, every entries here will be associated with a cofactor. So this is the cofactor C11 that's associated with this entry. This is the cofactor C12, so on and so forth. So if you construct a matrix, okay, so this is a matrix where every entries here is the cofactor for that particular entries that you have in a matrix A. So if you forgot what is a cofactor, you better review your videos. The first video where we talk about how do you compute the determinant. So now we construct a matrix C. This is called the cofactor matrix of A. So every entries here, A11, you compute the cofactor and put it here, and put cofactor C12, C1n, all the way to CNM. So you construct a matrix like that. This matrix is called the cofactor matrix. Okay, so now if you take this cofactor matrix, okay, and then transpose it. So transpose a cofactor matrix, meaning that you are interchanging the row. So you take this row and then place it as a column. You take this row and place this as a column. So this is going to be C transpose. So if you transpose the matrix, the transpose of your cofactor matrix is called the adjoint of A. So that's the terminology, okay? So cofactor, okay? And then you transpose your cofactor, that is going to call the adjoint of A. So for example, if you take your matrix A and then multiply the adjoint of A. So this is your matrix A, right? And then this is not the cofactor matrix. It is the transpose of the cofactor matrix. That's what adjoint means, okay? So for example, you can see that this row right here, is now this column, okay? You can see that this row right here is now this column. And you can see that this row right here is now this column. So you transpose your cofactor matrix. That is called the adjoint of A. Now, the key thing about this adjoint methods is this particular observations. If you take a matrix A and then you multiply your adjoint matrix, so this is your matrix A, and you multiply your adjoint of this matrix, which is C transpose, what do we have? Now, it turns out that if you multiply your A with the transpose of your cofactor matrix, so when you do matrix multiplication, so when you do this, okay, it will give you the determinant of A, all right? And when you do this, okay, it will give you 0. And when you do this, okay, it will give you 0. When you do this, it will give you 0. In fact, it will give you 0 for everything except when you do this, okay, except when you do this. So when you do this, you have the determinant of A, okay? Why is that so? Well, do you see that when you multiply this row and this columns using our matrix multiplications, this will give you this. A11 right? A11, C11, right? A12, C12, right? All the ways to A1n, C1n. And this is how you compute the determinant of A by doing cofactor expansions on the first row of the matrix. So if you have matrix A and this is your first row, all right, all the way to A1n. Remember, when you do your cofactor expansions, what do? If you do a cofactor expansion on this row, you will take A11 multiply C11 and then A12 multiply C12 all the ways to A1n multiply C1n. And this is the cofactor expansion along the first row of the matrix A in order to compute the determinant of A. So this is determinant of A. And you can also see that if you take this second row, multiply with this second column right here, you get A21. So now you see you get A21, C21, A22, C22, all the way to A2n, C2n. And again, that is the determinant, cofactor expansion along the second row of this matrix A. So this is how you compute the determinant of A by doing cofactor expansions on the second row of A. So every time when you have the second row and the second column, it will give you the determinant of A. If you do the third row and the third column, you also have determinant of A. If you do, say, for example, the n row together with the n column, you will have determinant of A. So the diagonal matrix here, the product, we know that the product of A times adjoint of A, all the diagonal entries, these are all the diagonal entries. You can also see that all the indices here are the same. So all the diagonal entries here will be the determinant of A. So that's the reason why you have determinant of A along the diagonal entries, because these are actually how you compute the determinant by using cofactor expansions. Now the question now is, I'm claiming that everything that is off diagonal, everything that is right here, okay, this is off diagonal. This is the one that is away from the diagonal. All those are going to be 0. So I'm claiming that, okay? So I am claiming that. So I'm claiming that if you take this, okay, multiply this, you get the determinant. But if you multiply this, you will get 0. If you multiply this, you will get 0. You'll multiply this, you will get 0. You'll multiply this, you will get 0. So let's just look at this example, okay? Just take a look at one of it. So if you take this first row, multiply this second column, so you see the indices will be A11, right? Then C21, okay, A12, and then C22, all the ways to A1n to C2n. I am claiming that this is going to give you 0. So when the indices here are different, okay, I'm claiming that this is 0. The question is why? All right, I will give you a moment to think about these problems, and you can pause the video. And when you think you have the solutions, you can restart the video, and I will be there, and we will be looking at the solution together. All right, welcome back. Now let's look at why this particular expression here will give you 0. Okay, so I wanted to show you that if I construct a matrix, so look at this matrix here. So look at the first row, okay, and the second row of this matrix. You see that they are the same. So the first row and the second row of this matrix, they are the same, okay? So now imagine that I am, so this is not matrix A, okay? So this is, let's call, I don't know, let's call it matrix P. Okay, so let's look at what happened when I do my cofactor expansion along this row. So I'm going to do my cofactor expansions on the second row, okay, of P. All right, so what do we do? So you will take A12, all right, so sorry, A11, and then you will compute the cofactor for this entry. So the cofactor for these entries is A21, all right? Okay, so, and then you take this. This is your A12, and then you do a cofactor expansion on this entry. So the cofactor expansion on these entries is A21, 22, sorry. And then at the very end, so ... and then the very end, if you do the cofactor expansion, you will have this entries A1n, and then you would do cofactors C2n. So this is exactly what we have right here. Okay, so this is exactly what we have right here: A11, C21, A12, C22, all the way to A1 and C2n. And this is the determinant of this matrix P. So this is the matrix P. So this is the cofactor expansions along the second row of P. So you get the determinant of P. Now, let's look at this matrix. What is the determinant of P? Well, you know that from the previous video that when you have a matrix which has identical row, okay, then the determinant of this matrix is 0. So we know that this determinant is 0, and since this is equal to this determinant and this determinant is 0, that's the reason why you have this 0. So you go back to this and you will see now the reason why this multiply this is equal to 0, because you are basically computing the determinant of a matrix that have identical rows. So why is this multiply this will also give you 0? Well, the answer is the same. All right, the answer is the same because this, okay, basically give you the determinant of a matrix which has identical row. That's the reason why there is 0. So even though we just explained one of these multiplications, but the rest of the rest of the multiplication give you 0 precisely because of that reason also. So now this is cool. So now you know that your matrix A multiply the adjoint of A give you everything 0 except those that are in the diagonal. So those that are in the diagonal, those entries are not 0. Those are all determinant of A. So obviously you can factor them out because this is the same as determinant of A multiply your identity matrix, right? So this is what happens. Okay, so this is what happens when you have this. So this is written like this. So now let's look at it very carefully. We have A, right? Okay, times the adjoint of A is equal to determinant of A times I. So let's say this matrix is invertible. So we have inverse. So let's say it's invertible. Then we know from the previous theorems that this is not equal to 0. So this is a number. So this is a matrix. This is a matrix, but this is a number and this is a matrix. Okay. So this is a number. This is a real number. Is non-zero. So I can divide. So because this is just a number, so even though when I divide, okay, it's supposed to be like 1 over determinant of A, but this is a number. I can move the number inside here. So I am going to put my determinant of A, 1 over determinant of A right next to adjoint of A. So now you look A, this is a matrix, multiply another matrix here equals to I. So let me say that again. This is A, this is a matrix, this is another matrix. So you have this matrix multiply this matrix equals to I. What does it mean? Well, it means that this matrix right here is the inverse of A. So you see that? So this matrix right here, this matrix right here, that's the inverse of A. Because this matrix multiply this equal to I. So by definitions, this is the inverse of A. So now we have a formula for computing the inverse. So A inverse is 1 over determinant of A times adjoint of A. All right, so how do you actually compute the inverse using this formula? Well, you have to find a cofactor matrix, and then you transpose that matrix, and then you divide the determinant of that matrix, and that's it. It's very easy to say, but it's tedious to compute. So let's look at the computation. So let's look at this example where the row reductions is not a very good method. Okay, so what we need to do is we need to find a cofactor matrix, okay? So the cofactor matrix here will be C11, C12, C13, okay, C21, C22, C23, C31, C32, C33, and you will have to find all these 9 numbers. Okay, so C11. So C11 is negative 1 to the power of 1 plus 1 minus 1, 1. So the minus 1, 1 will be, okay, cross away the first row and the first column and compute the determinant for this. So determinant of this will be this, multiply this gives you cosine square, and then minus this with this. So it will be plus sine square. So cosine squared theta plus sine squared theta equals to 1. That's the reason why right here you have a 1. And then find C12. So cross away this, find the determinant, okay, for this submatrix. Obviously, this is 0. So you can compute that. You can compute all the entries. So we know this is 0, compute this is 0. And by the way, once we have this, we can actually get the determinant pretty easily because you can see if you have that, this is all cofactor, right? So we haven't transposed anything yet. So this is cofactor. So determinant of A can be written as A11 okay, times C11, and then that's it. The rest are all 0. So you can see that A11 right here is 1. C11 is also 1. So immediately you know that this determinant of this matrix is actually 1. Okay, if you have the cofactor matrix, the determinant is just right there. It's very easy to find them. So if you find the cofactor matrix, okay, that's a cofactor matrix, and transpose them to get the adjoint, right? So this will become this, this will become this, this will become this, and then now the A inverse is 1 over determinant of A. In this case, it's just 1. Multiply the adjoint of A. The adjoint of A is this, so you get the A inverse as this. So I actually, it looks very easy. I actually computed a lot of stuff here. I didn't write everything down, but you do have to compute these 9 numbers. So in order to apply these methods, you have to compute these 9 numbers for the 3 by 3 matrix and also use that to find the determinant of A, and then you will get A inverse pretty easily like this. So the inverse of that matrix A is actually this. Okay, so remember in the very beginning we have this matrix A, okay, that we put into the augmented matrix like this and row reduce all the ways to I, and then we get that B, and that's B here is the A inverse. So now we are going to apply that to the get the inverse by using the adjoint method. So again, we compute the determinant of A. So I'm doing cofactor expansions along my first row, and you can see that what happened is the determinant for this matrix is -1. We need that, okay, and this also indicates that this matrix is invertible. So we use this formulas to find that. So we do have to find all these 9 numbers, right? So you see, we do have to find all these cofactors. So we have to compute all these things. So there's a lot of computations involved. Determinants, right? Because cofactor is basically a sign, positive or negative, of the minor, and the minor is the determinant of a submatrix, and in this case the submatrix will be a matrix of size 2 by 2, and you do all that and transpose your cofactor matrix to get the adjoint, and then A inverse will be given by this formula, which is this, and you can verify this is exactly the same as the A inverse that we get from row reductions. Okay, so now you have the formulas for A inverse. So this is true. Obviously, this thing here has to be non-zero, right? So because non-zero determinant gives you A inverse, right? So then you just have to multiply with the adjoint of A, and adjoint of A is the transpose of the cofactor matrix. Okay, so now we are going to give you a formula also. Another formulas to compute the solutions for a system of linear equations. However, I just want to point out that row reduction is still the best, because row reductions is the methods to compute the solutions for a system of linear equations. Because, not sure you realize this, you should realize this, is that determinants only works for square matrices. So if you have a matrix A that is not a square matrix, so this matrix is of size 4 by 3, so 4 row, 3 column, there's no concept of A inverse. There's a concept of left inverse and right inverse, but there's no concept of inverse. So we don't talk about left inverse and right inverse in this course, but the matrix is invertible, and the inverse and all that has to be on square matrices. And the determinants is not defined for matrices that's not square. Okay, so if you have a linear system that is 5 by 2, 4 by 3, we know that the row reduction method still works, okay? But what happens if they are 3 by 3, okay? You have a matrix A 3 by 3, 4 by 4, and all that. Then determinants is defined, and we can have some special formula for the solutions. And I'm going to show you one of this. So again, this is not the only things you can do, and most of the time we don't really do that. We just going to do row reductions, but sometimes people wants to have a formulas, right? A formula instead of row reduction. Row reduction is a procedure. It's difficult to describe a procedure. It's easier to give a formulas. So sometimes when people want a formulas, we can give them a formula if your linear system have a coefficient matrix that is square matrix. So if your coefficient matrix is square, so if you have AX equal to B, this is our matrix A, this is our vector X, and this is our vector B. So how do you solve this? So first of all, this matrix, you can compute the determinant. The determinant is 44, which means that this matrix here is invertible. So we know from before that if AX equals to B with the matrix A is invertible, then the system has a unique solution, right? Then the unique solution is precisely given by this. Okay, so we have a unique solution. All right, so why do we have a unique solution? Because this matrix A is invertible. We talked about that before. And so given that this matrix is invertible, the determinant is not equal to 0, so we can divide the determinant and so on and so forth. And we can write a formula for this. So we know that this system right here has a unique solution. So the solution will be x1, x2, x3. We can put them as a vector if you want to. But let's look at x1. We can actually find x1 by using these formulas, okay? I'm going to explain why we have this formula and how you actually use it. So obviously you see that we need to divide the determinant. That's straightforward. But what is this determinant? What is this determinant? If you look at this determinant is kind of like A. You see that the third row of A is actually right here. This is the third row of A, and this is the second row of B. But then this part right here is different. But then this number here is very familiar. This number here is actually right here. So what happened is that in order to solve x1, we take our coefficient matrix, okay, delete the first column and first column of A and substitute this B right into it. So you put your B, right? We are looking at AX equals to B and x1. So we are looking at the x1. So you'll put your B right here, and then you keep the columns of A. Okay, so the second column of A is here. So the second column of A is here. The third column of A is here. And then you compute this, and this will give you the answers for the x1. Okay, so that's what Cramer's rules is about. So we have a formula for that. Why is that true? Well, it's not very difficult. The books give you a different kind of proof, but I'm going to give you something that's easier. Okay, so we have generic matrix A. This is the X, and this is the B. All right. So in order to solve for X, okay, so in order to solve for x1, that's the formula. You can see that we substitute the entire B right here in the first column, and everything else we just keep it the same. Okay, now why is it true? Well, it is easy to see that this product of these two matrices will give you this. And again, don't multiply it out like that. Don't multiply everything out like that. It's very annoying. We are very sophisticated, okay? We already know how to multiply matrices. For example, we know that this A times this, right? You remember that very long time ago when we say A times the column vectors B1, B2, B3, for example, this is the same as AB1 as this column, AB2 as this column, AB3 as this column. We know that from before. So you can see that if you multiply A with this column, that's exactly this. That's the reason why you get this part right here. And we also know from the matrices properties for matrix multiplication, when you have this matrix multiply this, okay, so we don't do row operation now, we do column operation. This means 0 of this column plus 1 of this column and then plus 0 of this column. That's the reason why you have this. So we know all this property from before, okay? So this one right here is 0 of this column, 0 of this column, and 1 of this column, and you can see that's right here. So don't just do matrix multiplication like that. You don't see the pattern. So we know way more than that now. We are not in high school anymore. So we actually know some of the very important properties for matrix multiplications, and we saw that from the previous video, so we're using it. So we have that. So now, since this is this matrix multiply this matrix give you this, they're all square matrices. So remember that determinant of A times B, we proved that from the previous video, spent tons of time doing that. So now let's use it. So the determinant of the products of a matrix is the product of the determinant. So take the determinant here, that's determinant A. Take the determinant of this one, and you can see it's lower triangular matrix. So the determinant is nothing but the product of the diagonal. So the product of the diagonal gives you x1, and then you get that determinant. So now, okay, what is x1? x1 is this. Simple as that. So this is one easy proof that why Cramer's rules works. Okay, this is pretty straightforward. And I think you can kind of guess now that if you want to find x2, well, so keep this column, take this, delete this column, and put the b right inside here and compute the determinant, and you get the answer also. How do you prove it? Well, same thing. The construction is a little bit different, but you still take A. Okay, you take this matrix. So by eyeballing it, just look at it, you can see that this matrix multiplication is true. Again, this one obviously give you this. All right, this one obviously give you this. Okay, and this one obviously give you this. Okay, all right. So when I say obviously and you don't see it, you must try to review, because that's not good. Okay, which means that you are missing something. Okay, so this determinant is not, this is not a diagonal matrix, not upper triangular, not lower triangular, but it's easy to compute this determinant also. This determinant is actually just x2. Okay, so this determinant is just x2. For example, you can do your cofactor expansion along this row, and you can obviously see that you get x2. All right, so this is just x2, even though it's not upper triangular, lower triangular, or diagonal, but they have a lot of zero, so not a big problem to compute a determinant. So you have determinant of this multiply the determinant of this equals to the determinant of this. So therefore, you have your x2 equal to this. And now you will see, obviously, x3 is 1 over determinant of a multiplied this. You can see that this one here has been replaced by this. And again, the proof is also very similar. I shouldn't have mentioned it. You should be able to see why this is true now. So that's called Cramer's rule. People like it because some people like it. As I said, they have restriction though. If you are not square matrices, you can't use it. But there's people like it because that's a formula, right? There's no row reduction. There's no row reduction. It's just like, hey, this is the formula. Okay. Hey, this is the formula. So there's no reduction. You don't have to explain process, like row reduction process. You just like, I have a formula to compute x3. I have a formula to compute x2. I have a formula to compute x1. So sometimes people like it. So that's the reason why you will see Cramer's rule sometimes. And I don't want you to, next time when you see Cramer's rule in your computer science or engineering class, I don't want you to be caught by surprise. And actually, in differential equation, you actually use Cramer rules somewhere. And one part of it, you actually use a Cramer rule. So this is just try to tell you that instead of telling people a procedure on row reductions, we can give them a formula. But again, remember, there's restriction for that. This only works for square matrices. If you have known square matrices, there's no Cramer's rules. Your row reduction method still works though. So row reduction method is actually the best ever. But if you want formulas and your matrices are square, you can do it with Cramer's rules, okay? All right, this concludes our discussion on sections 2.3, and hence this also concludes our discussion on chapter 2, which is on determinants. So now we are going to make a huge transitions to chapter 4, which is a chapter on vector spaces. And this is the part where students usually have a lot of trouble with, because things is going to get a lot more conceptual. And by now you can kind of see that linear algebra is not really heavy on computations. We don't do integration by parts, integration by partial fractions. So in like calculus and differential equations, there's a lot of techniques on computations. But in linear algebra, our computation is really just row reductions most of the time, like solving system of equations. And we row reduces it to a REF matrix. And most of the time, you don't even have to do it by hand. You use a calculator to do it. So in this course, the more important thing is the conceptual understandings of a lot of mathematical idea, which might be new to you. So chapter 4 is such a chapter where everything is kind of new and abstract. And the computational part for that chapter, and actually for most of the chapter here, is pretty straightforward. As you can see later on, everything is kind of like hinges on the whether or not you can write down a linear system and row reduces it. And so the question is, how do you set up the system of linear equation? And that requires a lot of understanding. And that is what we want to do in the next chapter. So we will say more about it, but welcome to the abstract version of linear algebra. We're going to go into chapter 4, and we're going to start talking about vector spaces. We're going to talk about concept of linear independence. We're going to talk about the concept of spans, and so on and so forth. It's going to be very interesting, and this is the core part of linear algebra, and I hope you'll enjoy it. We'll see you very soon.